Chapter 7 Integrals. Integration is the inverse process of differentiation. Instead of differentiating a function, we are given the derivative of a function and asked to find its primitive, that is the original function, also known as antiderivative. Such a process is called integration or anti-differentiation. Let us have an example. What is the function which on differentiation with respect to x gives us 2x? So from the study of differentiation, we know that if we differentiate x square, what we get is 2x. Even if we differentiate x square plus 3, we will get 2x. Differentiate x square minus 0.5, what we will get is 2x. Differentiate x square plus 7 by 3, we are getting 2x. Differentiate x square minus root 3, we will be getting again 2x. Differentiate x square minus 100, again we will get is 2x. So there are infinitely many more such functions whose derivative is 2x. All these functions have the same derivative 2x because when we differentiate the constant term, we obtain 0. So what is the constant term here? X. When we differentiate this, we will get the differentiation of this as 2x plus 0, and that is 2x. Here also, differentiation of this will be 2x minus 0, and that is again 2x. Again here, differentiation will be 2x plus 0, that is 2x. So consequently, when we reverse the process, we have no idea what the original constant term might have been. So we include in our answer an unknown constant c called the constant of integration. We state that the primitive or antiderivative of integral of 2x is x square plus c. That is, we do not know if any constant is associated with the with x square or not. So what we'll write in general is x square plus c, where c belongs to r, because when we differentiate x square plus c, we will get 2x plus 0. C may be any real number, but the differentiation of c will be 0. So final answer will be 2x. So that will be the answer of our question. So when we want to differentiate function gx with respect to x, we use the notation d by dx as an instruction to differentiate and write d by dx. So this is the, whenever we have to differentiate, what we write is d by dx of the function. Suppose we have to differentiate gx, we write d by dx of gx. In the same way, when we want to integrate a function, say fx, we use a special notation, that is elongated s, fx dx. The symbol for integration is this. Elongated s is known as an integral sign. To integrate 2x, we write in this one, elongated s 2x dx equal to x square plus c. So the meaning of this question is the same as this one. What is the function which on differentiation with respect to x gives us 2x? So if you see that if you differentiate x square plus c, what we will get is 2x. So this question, and this is the symbolic way of representing this question. So both have the same meaning. Now let us go further in this. So this here, this elongated s is known as integral sign. Then 2x, that is the function which we are going to integrate, that is known as integrand. C is known as the arbitrary constant, and the final answer which we get is that is known as integral of 2x, or it is known also primitive or antiderivative of the function which we are going to integrate. Note that along with the integral sign, there is a term of the form dx which must always be written and which indicates the variable involved, in this case x. So sometimes students, they are writing only 2x. So that is the wrong way of writing, because unless you write dx, that means we are integrating this function 2x with respect to x. So that is the importance of writing dx. Without writing dx, it has no importance at all. It has no meaning. So it is a must to write this dx. So we say that 2x is being integrated with respect to x. The function being integrated is called the integrand. So already we have discussed that. Technically, integrals of this sort are called indefinite integrals. To distinguish them from definite integrals, so we'll learn later on what are definite integrals. Now let us recall what we have learned. So suppose there is a function fx whose integration we need to find. So integration of fx dx equal to fx plus c. This is capital Fx plus c. So this sign is known as integral sign. Fx, that is, this term is called the integrand. C is known as arbitrary constant. Fx plus c, that is the answer of this integration will be known as integral of fx with respect to x. Then dx, we have written here dx, that is the function fx is being integrated with respect to x. So now let us go through some more examples. Question number 1. What is the function which on differentiation with respect to x gives x square x? So if you know differentiation from the earlier topics, you may be knowing very easily that what is the function which on differentiation gives us x square x, that is tan x plus c. So the answer is tan x plus c. Also we can rewrite the same question as find the antiderivative of sec square x or find the integration of sec square x dx. So generally we will be using this form, that is, this is the symbolic form. So very rarely we will find questions of this type or this type, because these two have the same meaning, but we will be using only this form, that is symbolic form of integration. So now question number 2. What is the function which on differentiation with respect to x gives 1? So if you again recall differentiation, you will be knowing that if we differentiate x plus c, what we get is 1, because difference of x is 1 and difference of c is 0. So every time you have to write c, to write the constant, arbitrary constant c is a must. Then let us go in question number 3. Find the integration of e raised to x dx. So this function on differentiation will give us e raised to x, that is the function e raised to x itself. So we'll write e raised to x plus c, because c is compulsory to be written with the function. So this is what we have learned. Now let us go further in this. Let us learn some more integration formulas. First one, we know that the differential of x raised to n plus 1 over n plus 1 equal to x raised to n. So therefore what we will get is integration of x raised to n dx equal to x raised to n plus 1 over n plus 1 plus c. N is not equal to minus 1. Why n is not equal to minus 1? Because if n equal to minus 1, the denominator will be here minus 1 plus 1, which is 0, and that is not possible. In particular, if we differentiate the function x with respect to x, we get 1. So we can say that the integration of dx or the integration of 1 dx is equal to x plus c. Same way, let us see the second part of this formula. If we differentiate sin x with respect to x, what we get is cos x. So therefore, we can say that the integration of cos x dx is equal to sin x plus c. Third one, the differentiation of minus cos x equal to sin x. So if we integrate this sin x, what we will get is minus cos x plus c. So this is what we are getting here. Integration of sin x is equal to minus cos x plus c. Now let us check the fourth one. Differentiation of tan x is sec square x. So if we integrate sec square x, what we are going to get is tan x. So that is integration of sec square x dx is equal to tan x plus c. Same way now, we'll just learn the formulas, and these formulas will be very, very important for solving any of the problems in which they are applicable. So integration of cosec square x dx is equal to minus cot x plus c. Integration of sec x tan x dx is equal to sec x plus c. Integration of cosec x cot x dx is equal to minus cosec x plus c. Then integration of dx over root of 1 minus x square is equal to sin inverse x plus c. Integration of dx over root of 1 minus x square equal to minus cos inverse x plus c. Integration of dx over 1 plus x square equal to tan inverse x plus c. Integration of dx over 1 plus x square equal to minus cot inverse x plus c. So these are very, very important formulas, and some more are here. So integration of 1 by x dx over root of x square minus 1 equal to sec inverse x plus c. Integration of dx over x into root of x square minus 1 equal to minus cosec inverse x plus c. Integration of e raised to x is e raised to x plus c. Integration of 1 by x dx is equal to log modulus of x plus c. So whenever we are writing the integration of 1 by x dx, it is a must to keep the we are getting log mod of x plus c. So keep that x in mod. Then integration of a raised to x dx is equal to a raised to x over log a plus c. So these are very important formulas of integration, and there will be many more. These are not the only formulas. We have to learn them thoroughly so that you will not find any difficulty in solving problems based on integration. Let us learn some properties of indefinite integral. The first one is the process of differentiation and integration are inverse of each other in the sense of the following, that is, if we differentiate integration of fx dx, what we will get is the function fx, that is the differentiation d by dx and the integration fx dx, they will cancel each other and we will get the function fx. And integration of f dash x dx is equal to fx plus c, where c is an arbitrary constant. So this is property number 1. Then we have the second property. Two indefinite integrals with the same derivative lead to the same family of curves, and so they are equivalent. So now third one, integration of fx plus gx dx is equal to integration of fx dx plus integration of gx dx. Fourth one, for any real number k, integration of k fx dx is equal to k into integration fx dx. That is, we can take out k out of the integration. So this is fourth property. Then fifth one, it has been extended. That is integration of k1 f1x plus k2 f2x plus so on till kn fn x dx is equal to k1 integration of f1x dx plus k2 integration of f2x dx plus so on till plus kn integration of fn x dx. So this is our property number 5. So we have discussed all the properties, and now let us learn something more. Comparison between differentiation and integration. First one, both are operations on functions. Both satisfy the property of linearity, that is d by dx of k1 f1x plus k2 f2x is k1 into d by dx of f1x plus k2 d by dx of f2x, and same way we can distribute here also integration also. Integration of k1 f1x plus k2 f2x dx is equal to k1 integration of f1x dx plus k2 integration of f2x dx, where k1 k2 are constants. Third one, all functions are not differentiable. Similarly, all functions are not integrable. Fourth one, the differentiation of function when it exists is a unique function. The integral of a function is not so, because you may have already seen that. Initially, what example we have taken, integration of 2x dx. So what we initially took, if you remember that, 2x dx, and the answer was x square plus c. So this is not a unique function, because if we take here x square plus 3, we will get it another function. If you take x square plus 5, then that function will be different one, though they will be all the same family of curves, but x square plus 3 will be different from x square plus 5. So that is what it is here. The derivative of function when it exists is a unique function. The integral of a function is not so, because suppose we differentiate x square plus c, we get only one answer, that is 2x. But when we integrate 2x, we get many answers. That is why we write here c. So x square, we get in fact a family of curves. So we write as x square plus c. Now fifth one, when a polynomial function p is differentiated, the result is a polynomial whose degree is 1 less than the degree of p. When a polynomial function p is integrated, the result is a polynomial whose degree is 1 more than that of p. So this one we have seen in the formula itself. Here we have gone through the formula of integration of x raised to n dx. We can see that here the exponent of x is n, and here it is x raised to n plus 1 over n plus 1. The exponent in this case n plus 1. So the exponent has been increased by 1. Whereas if you see the differentiation, what is the exponent here of x n plus 1? On differentiation, it is being reduced by 1, because n plus 1 minus 1 is n. So this is the difference between differentiation and integration. So that is what the property they have mentioned there. And now let us go again in the same list of properties. So sixth one, we can speak of the derivative at a point. We can never speak of the integral at a point. We speak of the integral of a function over an interval on which the integral is defined. So it is not at a point. It is in fact in the whole interval. Then seventh one, the derivative function has a geometrical meaning, namely the slope of the tangent to the corresponding curve at a point. Similarly, the indefinite integral function represents geometrically a family of curves called parallel to each other, having parallel tangents at the points of intersection of the curves of the family with lines orthogonal to the axis representing the variable. So this one will go through, we'll learn with the help of the figure that will go at the end of this when we go through all this till the 9th points. So 8th point is the derivative used for finding some physical quantities like the velocity of a moving particle when the distance traversed at any time t is known. Similarly, the integral used in calculating the distance traversed when the velocity at time t is known. So they are opposite to, they are inverse of each other. Here uh, the derivative used to find the velocity, and integration is used to find the distance. Then the ninth one, differentiation is a process involving limits. So integration as well, we will see in the later section. And this 10th one is, we are having the process of differentiation and integration are inverse of each other. Already we have seen that. Now let us go through this uh, point which we are discussing here. Seventh one, that is, the derivative of function has geometrical meaning, namely the slope of the tangent to the corresponding curve at a point. Similarly, the indefinite integral of a function represents geometrical family of curves, not one curve but a family of curves placed parallel to each other, having parallel tangents at the point of intersection of the curves of the family with the lines orthogonal to the axis, representing the variable of integration. So here we have a graph for that particular property, and you can see here. So this is the function. Initially, when we started the topic of integration, we have taken the function 2x, which was to be integrated. So the answer which we got was x square plus c. C is here an arbitrary constant, and we have learned that what we get is actually not one function but a family of curves. So this is what we are getting here. C can have any value. It can have the value 3, it can have the value 2, 1, 0, minus 1, minus 2, minus 3. There are infinite functions of the type x square plus c. Some of them have been shown here. So what that remark says, that if we draw a line parallel to the, what is the variable of this function, that is x. If we draw a line perpendicular to the x-axis, that is the axis of the variable, what is that, x. So wherever that perpendicular line cuts the family of curves, here it is, you can see that p minus 3, p minus 2, p minus 1, p0, p1, p2, p3. And if we draw tangents at that point, they all will be parallel. You can see here tangents drawn at p3, p2, p1, p0, p minus 1, p minus 2, p minus 3. So they all are parallel. So this was what was the meaning of that particular remark that we have gone through, that is uh, this point number 7, that is the derivative of function has a geometrical meaning, namely the slope of the tangent to the corresponding curve at a point. Second part of this. Similarly, the indefinite integral of a function represents geometrically a family of curves. We have seen that in the figure, placed parallel to each other, having parallel tangents at the points of intersection of the curves of the family with the lines orthogonal or perpendicular to the axis, representing the variable of integration. So you have to remember all these properties and remarks and the formulas which we have learned. So they will be very, very helpful to you to solve problems in which they will be applicable.